Hey guys, today I'm going to solve a problem from Faraday's law. In this question we have a rectangular loop of length L and width W, and that has total resistance of big R, and the question says that this loop moves away with a constant velocity V from infinitely long straight wire that carries a current I, and the question is asking us to find the magnitude and direction of the induced current when the lower end of this loop is at its distance small r from this wire. So for solution we need to find the induced current, which is induced EMF divided by resistance is big R. Now we need to find the induced EMF. We can use the Faraday's law, which says that induced EMF along a round trip path, which is this rectangular loop, is equal to the rate of change of the magnetic flux given by this relation. So for that we need magnetic flux. Magnetic flux is given by this relation right here, surface area integral, so integral B dot N dA. So for this we need the magnetic field by this wire. So if you are given a data sheet, the magnetic field at a distance r by a long wire, infinitely long wire, is mu naught I divided by 2 pi r. Since we are not given this relation in this formula, in this question, we are actually gonna derive this relation. So for that, let us consider circle of radius S centered on this current carrying wire. So after you do that, by the Amperian loop, we have this relation. This is closed path integral B dot dl is equal to mu naught I. So B is the magnetic field and our path is circumference of the circle, 2 pi r. S is the radius, so 2 pi s is equal to mu naught times I is the current. So B is equal to mu naught I divided by 2 pi s. So if you use your right hand rule and if you point your thumb toward the direction of the current, if you curl your finger around the wire, your finger should go into the page, so magnetic field is into the page. So now after you calculate the magnetic field, you pretty much go and plug in and do the math for rest of them. You calculate the flux, which is given by this relation, so our integral. So now you need to find the limits of integral, because you need to find the flux around the whole area. So from this wire you have from R to this end to this end. So if you see from this wire, so it is from R to R plus W. So you have your integral from R to R plus W. B is given from here, so your area is length times breadth. So breadth is the distance moved with a constant velocity V, which is ds, we are assuming. So if you do your integral, you get this is pretty much math from here onwards. So now after you calculate your magnetic flux, you go and use that magnetic flux for induced EMF. So induced EMF is derivative of or negative rate of change of the change in magnetic flux. So for that you need to calculate the derivative of this part, which I have used the chain rule to calculate it. You can pretty much follow the math, and this is the derivative r over r plus w times negative w over r square times dr by dt. So after plugging in this into the induced EMF formula, right, induced EMF form right here, you get negative mu naught IR divided by 2 pi times negative w over r square times r over r plus w dr by dt. dr by dt is time rate of change of distance, which is the velocity. So your induced EMF is mu naught IL divided by 2 pi times V times W divided by R times R plus W. So your induced current is this EMF divided by R, and this is your form right here. Now for the direction, magnetic flux is into the page and it is decreasing because your loop is moving away from the wire, so it gets weaker. And by Lenz's law, your induced current, which is the induced current that produces the magnetic field, always opposes the change in the magnetic flux. Therefore the induced current should be clockwise, and it is producing a self flux that is positive into the page to cancel the change in magnetic flux. Thank you.